Hello, everybody. Welcome to the week 3 lecture. So now we are in module 2, and this is week 3 of the course. This week we're going to be discussing structural systems of buildings. All right, so our readings for this week are going to be chapter 4 from the Bengali book, and then also the structural systems section of the Ballast book that I will have posted to the module folder on Blackboard. The notes for this week, they're mostly out of the Bengali book, but I've also included some of the key highlights from the Ballast reading as well. So this is going to be a little bit of a mix of the two, but for the most part, the structure and formatting that I have in here is going to follow what's in the Bengali book pretty closely. So all the headings and things like that should line up pretty well as you're sort of going through this and doing your readings. All right. The Bengali book gives a really good sort of overall general look at all the topics that we're going to be talking about in this chapter. But the Ballast book provides a lot more detail in terms of specific things that you're going to need to know as an interior designer related to practice. So it's, I think, really important for you to read both and maybe read the Ballast book after you read the Bengali book, because you'll sort of get that general background with what's in the Bengali book. And then when you read the Ballast book, it just goes into more detail and it'll be a lot easier for you to sort of understand and follow. All right. Because that's geared more toward people who are looking for their certification. So they should already have a little bit of prerequisite knowledge of the topics. Anyway, let's get started with the introduction. This is a really long chapter in terms of the content that's in here. So we'll try to get through this as quickly as we can, but there is quite a bit here in these notes. So interior designers do not need to have an expert level knowledge of structural systems, but they do need a basic working knowledge of them to be effective at their jobs. All right, this is very similar to what we talked about in Module 1. In terms of building systems in general, you don't have to be an expert on all these things, but you have to have a base level knowledge of it because it's just part of your job and it's things that you're going to be dealing with, and you're going to have to coordinate with people who are experts on these things. So you have to understand sort of in a general way how these systems go together and they work together, but you don't have to be an expert. All right, you just have to have a basic working knowledge and understand the terminology and things like that. All right, so you don't really need to do a deep dive into all this stuff. Interior designers need to have enough knowledge of structural systems and elements to be able to read and interpret architects' and engineers' drawings in order to make informed design decisions. Okay, so as we'll see a little bit in this chapter and probably more so later on in the course, you will have to be able to read and interpret drawings that you get from these really technical people. Okay, and you're going to be coordinating with these people in order to determine what goes on in those drawings as well. So it's important that you understand the systems so that when you're looking at these detailed construction drawing sets, you understand what you're looking at. All right. Situations where this knowledge is important. Is a structural element, or is an element structural and would moving it be feasible? Can floor, this should say penetrations, not partitions, be made? Is building movement expected, and how can it be accommodated? Is a structural review necessary for the proposed new floor loading? How should interior design or interior construction elements interface with existing structural elements? And will fire protection of structural elements need to be repaired, or should new protection be included in the design? Like I said, interior designers must also develop appropriate vocabulary in order to effectively coordinate with architects and engineers. And interior designers will likely encounter a wide variety of structural systems So it's important to be familiar with as many as possible. So when you're out working, you're going to have just a bunch of different types of projects that you'll be doing and a bunch of different buildings, and more likely than not, they will all be sort of a different structural system in each type of building. So I mean, they will be very similar, but there will be nuances. And for example, if you're working on like a commercial office building, that's going to be one type of a structural system. Or if then you go on and you start doing residential work, that's going to be a totally different type of structural system that is holding the house together. So it's important that you kind of understand the differences and understand what to expect for the type of building you'll be working on. All right, let's go on here. So here's a basic intro to structural systems. Structural systems are systems that are designed and constructed to support loads that are applied to the building and transmit them safely to the ground without damage to the building. Okay, so it's going to take all of this weight that is being generated by the components that are a part of the building, and its job is to hold the building together, but also take all that weight and transfer it down to the earth, where it kind of is being supported. All right, structural components protect the building's occupants and contents. All right, that's another thing. It keeps the building together, and it makes sure that everything inside the building stays safe. All right, it's just like a skeleton. Okay, like a skeleton, like our rib cage, that's going to protect our vital organs, our heart, for example. Same thing with sort of a building structural system. Structural systems can be composed of a single material or multiple materials. Okay, so for example, heavy timber structures are usually composed of wood, obviously, and then steel structures are typically composed of metal and concrete. Buildings can be composed of multiple structural systems as well. So, for example, a concrete foundation will support a wood-framed superstructure. All right, so if you look at this little diagram here, this is from your textbook, you can see we have our foundation, which is usually made of like a concrete or some type of a masonry at the bottom supporting the rest of the building, and then this above it, everything above the foundation is what's known as the superstructure. All right. Often materials that appear to be structural are actually cosmetic. So for example, a building with a brick exterior might have concrete or steel structure behind that brick that actually is what's carrying the structural load of the building. All right. The superstructure, like I said, that is the part of the building that sits on top of the foundation. So that includes elements like columns, beams, and load-bearing walls to support roof and floor assemblies. The foundation is the part of the building that is in direct contact with the soil, rock, and groundwater, and that is going to transfer building loads to the earth. And it also serves as a way to keep the building's superstructure, so everything above the foundation, dry. Foundations are typically constructed of concrete or concrete masonry units, which is CMU. We're going to talk about CMU a little bit more later on in the chapter. There are several different types of foundations, okay, including full foundations, crawl space foundations, slab foundations, and pier foundations. Basements, so I'm sure everybody knows what a basement is. If you don't, that might be a little bit concerning, but a basement is going to be a fully accessible space underneath the superstructure of a building that is located within the walls of a foundation. All right, basement temperatures remain within a narrow range year-round. Okay, so the temperature down there, the air, is going to be pretty consistent year-round just because it's underground. Basement floors are typically made of concrete slabs. Crawl spaces, so these are areas underneath the superstructure of a building that are too shallow to stand or even sit. Okay, so a crawl space similar to a basement, except the main difference is there's not enough room to actually make the space inhabitable, so you can't like stand down there or anything. It's literally just used to provide access to electrical, plumbing, and mechanical equipment. And they should also be ventilated to combat moisture that's going to migrate into them from the ground and from the building's interior. So crawl spaces, they aren't really going to have concrete slabs as their floor to sort of block moisture. So they're a lot more open, and they have a tendency to get moisture into them. So like this is saying, they need proper ventilation in order to stay dry and combat that moisture. Here is a really interesting video from a home builder that I follow on YouTube, and he goes into detail about different types of foundations. So you can watch that. It's kind of a little bit longer video, but it's really interesting if you want to learn a little bit more about them. All right, so these next few pages, I have these diagrams of these different types of foundations, and hopefully this will explain them a little bit better if you have never seen these types of foundations that we're going to be talking about. So first we have what's known as a slab foundation. It's also called a slab on grade foundation, okay? And this is a foundation of like a house where there's no basement. So literally all it is they just pour the concrete slab directly on top of the grade, okay? So they don't really excavate down at all. They just basically put it right on top, and then you can see it goes down a little bit, but not nearly as much as what it would be for regular foundation. And then they just build the superstructure of the house directly on top of that. All right. This is it showing it in a heated building with the insulation. So the insulation is going to be represented by this this pattern that's here within the pig space. That's the standard pattern for batt insulation on construction drawings. And then this one down here, obviously there's no insulation. It's not a heated building. All right, the next one, this is a crawl space foundation. So like I said, this area right here is the crawl space. Okay, so obviously it's not tall enough to be able to stand in or maybe even sit in, but you could crawl into it and have access to things like electrical or plumbing that's running underneath of this flooring here. This little blue line that you're seeing here, this is representing a vapor barrier. So a lot of the times they will install vapor barriers directly over the like the soil in this case, if it's not able to be ventilated. And that's going to basically just block all the moisture that's wanting to seep up into the crawl space from the ground that's below it. All right. You can see here's the foundation wall. That is made up of CMU in this case. So CMU, concrete masonry units. These are basically concrete blocks that are stacked on top of each other. And they only go a little bit of the ways up above the soil. And then your superstructure sits on top of that. And basically everything else is just built up from there. This right here is a full foundation. So this is probably what you're most used to. It's probably the most common one, I would say, in this area. So in terms of just like a residence, usually these just have a full foundation. And these are when you have houses that have basements. Obviously, most of us have basements. Yeah, you probably have a full foundation. Okay, so this is basically very similar to what we're seeing here on the crawl space, except it goes a lot deeper. And so here you can see the wall is extending all the way down. Usually they try to make this below the frost line, if you've ever heard that term, to prevent like freezing and stuff like that. But basically this space right here is the basement, and then in front of the basement wall, it really depends on if this is supposed to be like a finished space or not, but in this case, I'm assuming this is supposed to be like a finished space down here. They will actually build a wall in front of the concrete wall right here, and You can see this wall is insulated. They have like a baseboard and stuff on it, and then there looks like a drywall ceiling. But then on top of that, we have our superstructure, okay? And the superstructure is going to be bolted directly into this concrete or CMU or whatever it is that the foundation is made of, okay? So you can see a little anchor bolt right there that's coming down. So that's going to be embedded 7 inches at minimum into the foundation wall, and it's going to be spaced 6 inches on center. Within 1 foot of the corners, okay? So there's a set standard or like a code requirement in terms of where these anchors are being placed into the foundation. All right, so then the last one, the last main one that we're going to be talking about is a pier foundation. These are common in like areas where there's a lot of like moisture or risk of flooding. So maybe down south, maybe in like Louisiana, places where like they get hurricanes and stuff like that, they will have pier foundations. So basically you can think of this as like stilts for the house. This space underneath right here where there would be like a crawl space or a basement normally, this is just open. So you can see this grass, for example, is like within it. Okay, so this is just open space, and it's basically just a set of piers, right, or stilts that the house is kind of sitting on top of, and then the superstructure is just anchored to this. But they do this so that the house can sit higher up off the ground and it won't get wet. For example, if there's flooding, there's nothing down here that's going to get wet from all that water, all right? All right, so the next topic is building loads. So building loads refer to the variety of forces that are acting upon a building structure. A building is basically undergoing all kinds of stress, and that has to be factored in when architects and engineers are determining the design of the structure, okay? So there's all kinds of calculations that they have to do, but basically all of these types of loads we'll be talking about here are things that they have to take into account, and they have to calculate in order to make sure that there's not going to be like a structural failure down the line, okay? So types of building loads. So there are what's known as gravity loads. I think this is what is mentioned in the ballast book. They kind of categorize these things in different ways, but it's basically anything that has weight that's being affecting the structure. Basically, the weight of whatever component is within the structure that is affecting it. Okay. So a dead load. That is a load which acts vertically downward on a structure, and that also includes the structure itself and also any components that are permanently attached to it, okay? So for example, columns, beams, exterior, interior walls, floors, lighting fixtures, mechanical equipment, all those things are permanently attached to the building, and that's all weight that the structure of the building has to carry and transfer down to the foundation. Normal dead loads are factored into a design on a square foot basis. Okay, so they have this calculation that they do, the engineers, structural engineers. They're going to determine dead load requirements based on like a square foot basis. So it's going to be a certain rating, like, I don't know, 2 foot per square foot, for instance. I'm not sure if that's like an accurate measurement or not, but I'm just saying they're going to calculate it based on that and make sure that the structure per square foot can handle whatever they kind of determine is necessary for the application. Static loads. So these are loads that are applied slowly and steadily to a structure until they reach a maximum. So for instance, this will include the weight of the structure itself, the weight of building elements, fixtures, and equipment permanently attached to it, and movable or moving live loads. All right. This is how the book describes the two of these. Really, they're pretty similar in terms of what they are, just maybe some slight nuances to them. Live loads. So these are loads that are going to gradually be changing over time. So this is going to include things like the weight of a building's occupants. So all the people inside the building, they're going to be coming to a building and then they're going to be moving throughout it. Okay, so that's always going to be changing depending on how many people are in the building at a given time. So they have to take that into consideration too, and they have to consider occupancies and maximum occupancies, and they have to design around the maximum that the building can hold according to code. Okay, occupancies, that should have been something you learned about in your codes course in the past. Basically, they will refer to that, and then they will determine, kind of based on the program requirements of the building, what kind of live load calculation do we need to factor into the design. Live load accommodations are determined by a building code based on occupancy type, like I said. For example, the floor of a residential apartment building would have a lower live load requirement than a commercial office building. So obviously a commercial office building, that's going to have a lot of heavy desks, a lot of heavy equipment involved, printers, servers, stuff like that weighs a lot. So they have to allocate a lot more sort of structural support into the structural system for commercial office building than they would just like a regular old residential apartment building. Dynamic loads. So these are loads that are applied suddenly to a structure, often with rapid changes in size of the force of the point to which it is applied. So for example, like an earthquake or wind. All right, something that is just sort of happening really quickly and then it goes away. The building needs to be built in order to withstand sort of the unexpected. So here's a little video on building loads. This is kind of like a more scientific, detailed video about it, just so you can understand what the different types are. Next, we're going to talk about compression, deflection, and tension. Okay, so these are all forces that are acting upon the structural elements of the building. Compression, so this is a shortening or pushing together of a material resulting in a reduction in its size or volume. So for example, when you sit on a sofa cushion, obviously you're going to be compressing the fibers of that sofa cushion together, and if you sit on it enough times, over time it's going to maybe sag or it's going to lose its original shape. Okay, so you're compressing things together and you are altering its form or its shape. Obviously, compression can cause deformation to occur. That's kind of what I said. And then deflection, this is a measurement. Okay, so this is the perpendicular distance that a beam is bent down when a load is placed on it. Okay, and then lastly, we have tension. So this is a force caused by stress that stretches or pulls a material along the direction of its length. All right, so this is the picture from the Bengueli book, and basically what you're seeing here, we have, let's say, two columns or exterior walls, and then you have a beam that is spanning the two of these. Okay, let's say we have a floor above this, and all the weight that floor is carrying is going to be applied to this beam. Okay, and it's going to bend the beam downward to some degree. That measurement of how much the beam is being measured downward, okay, if you look at this line right here, think of that as the beam with no pressure applied to it. Then we apply pressure, it bends it down and it bows it slightly. So the distance between the original point, the original top point of the beam, and the new location of the top of the beam, that is your deflection measurement, okay? Now, if we look at these other two terms we're talking about here, we have compression and tension. So as the load is being applied, you can see the top side of the beam is experiencing compression. So it's being pushed down, and the fibers here toward the top, they're being pushed together, okay? And then at the bottom, the fibers at the bottom of the beam, these are actually being spread apart. Okay, I think this makes a little bit more sense if you look at this example right here. This is basically the same thing, but you can see the fibers at the top are being compressed, and then there's basically this neutral zone here where nothing is really going on, and then the fibers here at the bottom are being spread or pulled apart as whatever the load is pushing down on it. And then if this becomes too great for the beam to withstand, that'll result in a failure. Okay, so this is where the beam actually breaks, and you can see here these fibers right here being smushed together, and then these ones are being pulled apart, so you can see actual airspace between here, right? Because it's being pulled and this is being pushed together. All right, hopefully that makes sense. Okay, spanning openings. So beams, you should be familiar with what a beam is. That is a horizontal structural member that is longer than it is wide or deep. So a beam can be bent downward by compression, like we said. The distance between a beam support is called its span. Okay, so if you look down here, we have a support on one end here and a support on the other end here, and the distance between those two supports is known as the span. Beams can come in many different shapes and sizes, and they can be made of different materials such as dimensional lumber or steel. Okay, this right here is just an example of the different types of beams that you can have. So we have a regular, just plain old wood beam. This was milled from just a tree trunk. Okay, it's just a solid piece of wood. Then if you need extra strength, they can take beams and they can basically sister them together. And this can be done by laminating them, laminating layers together. So that's something called glue lam. I think the textbook mentions glue lam. Or they might also like bolt them together in certain cases. It just depends on the application. Sometimes these are even, you might have wood. So you might have two pieces of wood on the outside, and then the middle layer is actually a plate of steel. Okay. But basically the term that they use is laminated. So they will laminate these different components of the beams together. Right here is a spaced beam. So this is basically two pieces of wood. You're seeing the ends of them, and then the space in between here is basically like open space. Okay, and also what you're seeing here in these pictures, in case you don't know, these are sections of the beams. Okay, so these are cross sections. Anytime you see an X on a piece of like wood in a drawing, that is telling you that you were looking at the cut end of a piece of wood. All right, and then here we have a box beam. Okay, so these are just two pieces of wood basically on top of each other, and then on the outside, the outer layers are basically like pieces of plywood that they have sandwiched. So they're sandwiching these two pieces of wood that are inside. We also have another type, which I think is shown in it's shown in the textbooks for sure, and that is like basically an engineered beam or an I-beam, I think they might refer to it as. But that's sort of like this, what you're seeing here, except the layer of plywood is actually running in between the top and bottom. All right, you'll know what I'm talking about when you see it in the book, but those are like engineered beams. And actually, there's an example of it later on in this document too, so I'll point that out. Then we also have steel beams. Okay, so these are kind of steel I-beams, right? I'm sure you've seen these before if you've ever seen like a commercial construction site where everything is made out of steel. They will have these beams, and they come in all different shapes and sizes depending on what the application is. So moving on, we have trusses instead of beams. Okay, so trusses are structural members that are or that use the inherent stability of triangles to support a load. The structural members that make up a truss are always in tension instead of tension and compression like beams. Okay, so the way that trusses are engineered, I'm going to flash to this really quick. This is what I mean when I'm talking about a truss. They're engineered so that you have these angles, these triangles, and these are always holding the structure of the truss in tension. Okay, so like a beam that's being subjected to both tension and compression. They're only being subjected to tension. All right, which is a little bit better for the structure. It's a little bit more stable. They are common components of roof assemblies, and they can be made of wood or steel. Okay. Laminated wood trusses. So these are trusses that are made up of smaller pieces of wood, and they are glued together into large trusses. They are engineered to be stronger than solid wood trusses. Okay. So again, here's our truss. Some basic terminology. This piece of wood that's running along the bottom, that is our bottom chord. And then these two pieces of wood that are running at the angles, these are top chords, okay? And then we have what's known as our pitch. So basically what we're seeing here is rise over run. Your pitch is going to be determined by taking the rise and dividing it by whatever the required run is. Okay, and that's going to give you your angle here. It's going to give you your roof pitch. Lintels, arches, and corbels. Okay, so a lintel, that is a horizontal structural member placed over a door or a window, and the purpose of it is to transfer the load from around the window opening, okay? And these can be made of concrete, steel, or wood, and if they're wood, they're going to be called a header. Okay, so that's probably a term you've heard before. Headers, that's probably what they're more commonly called. Arches, these are curved openings that are frequently used decoratively and expressively, and they're found in many historic architectural styles. Okay, so here is an example of a Roman arch. You can see the way that this works is all these blocks basically are pushing against each other, sort of inward, and it just helps them. It allows them all to be self-supporting, just the way that this is engineered. Okay, and then all the load is being transferred between them, and it's going down through these side walls down to the ground. Corbels. So these are masonry units that are stacked with each row extending beyond the row below. They are held in place by the weight of the construction on top of them, and often they're used as a decorative detail on brick exteriors. So this is the example from the textbook. The corbel is basically this little zigzag here and here. Okay, so you can see we have some block or some brick or some CMU or something, and there's the opening. And these are extending out halfway beyond the brick below, and again halfway beyond the brick below, and then we just have a full course of bricks on top of that, and it just works. Okay, so it's being held in place by whatever is above it. Basically, it pushes it down, and the weight is enough so that it's not going to move in any way. And here's an example that I found online. When I think of corbels, I think of this decorative detailing that you'll see in some fancier masonry buildings, but basically they use it in a decorative way to add visual interest to the facades of masonry exteriors. Vaults. Okay, so a vault is basically an arch ceiling structure, and it's made of stone, brick, or reinforced concrete. Barrel vaults, these are basically an arch that has been extruded. Okay, so if you have your basic arch shape and then you just extrude that back, now you have a barrel vault. A groin vault is basically taking two of these barrel vaults and intersecting them at a 90-degree angle. So you have one barrel vault going this way and one going this way. And their intersection creates this sort of intricate shape that you're seeing here. This is common in a lot of, I don't know, maybe European style buildings. So a lot of older style buildings, classical architecture, they will have barrel vaults and groin vaults. And if you go to Italy during your third year, you decide to study abroad over there for the semester, you're probably going to see a lot of these types of openings. Then we have domes. Okay, so a dome is just a hemispherical structure, and they usually form a ceiling or a roof. So here's just an example of a dome from an interior. Cantilevers, these are horizontal structures that extend out beyond a support. The weight of the cantilevered structure and any load that is on it is then transferred back to the supporting wall. So for example, like a diving board, okay? Here's an example here of it used on a building. So you have this basically cantilevered structure that's hanging out all the way past this big concrete supporting wall here. And the structure of this supporting wall is really important because it has to hold all this weight, okay? Like there's nothing out here even holding that at all. So for that to be possible, they have to engineer this structural wall here and make it really beefy in a way that's going to be able to hold all this weight, right? Vertical supports. So columns, these are vertical structural members that are longer than they are wide or deep. Columns are compressed by loads that are placed on top of them. If a force acting upon a column is too great, the column may experience a structural failure. Okay, so you can see just like a beam, as a load is coming down on top of this column, we can get some deflection in here. So this is the original column before it had any load applied to it. Then as it's coming down, this is causing the column to buckle, and you get some deflection here between where it was originally and where it is now. And if that becomes too great, if the load is too much for this column to handle, it's going to buckle all the way. It's going to collapse, and it's just going to fail and not work. Columns are intended to transfer structural loads safely to the ground, so very much like a load-bearing wall or something like that. And well-designed columns can handle loads that are greater than those anticipated in normal use. Okay, so if you're in a building that has columns, most likely that column can handle a lot more weight than it is currently, but just to be safe, they will over-engineer the column so that if anything were to happen, you don't really have to worry about the column failing, okay? A colonnade. So a colonnade is basically just a row of columns that are connected to one another by arches. And then a pilaster, this is a type of column that protrudes from a wall, and these are used to strengthen walls from the impact of lateral forces. Okay, so any type of force that's coming at the wall sort of from a perpendicular direction, so like wind, if there's like a wave, like if there's flooding and a wave hits it, anything like that coming at it perpendicularly, a pilaster is basically there to beef up that structure of the wall and protect it from any of those lateral forces that are going to be hitting the exterior of the building. So here you can see this is a pilaster, and it's just two columns, basically that's what it looks like, that are protruding out of the stone face of this building. Load-bearing walls, okay? So load-bearing walls are just walls that are designed to spread structural loads over their entire surface. This video here gives an explanation of load-bearing walls. This one's a really interesting This Old House video. He basically has a model of a framed house, and he's going to explain how to identify load-bearing walls and what you need to do to basically remove a load-bearing wall, but that's a really interesting video if you want to watch it. Lateral forces. So a lateral force is applied to an element in a perpendicular direction, or a direction that's perpendicular to that of support. And basically to counteract these lateral forces, you can use bracing elements. So these are known as lateral supports. So if you look at this pergola picture right here that I have, right here, this diagonal member that's going across here, that's connecting the vertical member and the horizontal member, this is a corner brace, and the whole purpose of that is to provide some additional support against these lateral forces. So if wind hits this pergola and there's no bracing element here, and the force of the wind is too strong, this whole structure, this connection here could fail and it could all just topple over. So by connecting the two of these together with a diagonal brace, that is going to significantly strengthen this connection and reduce the likelihood that that's going to happen. Lateral stability. So this is the ability of a structure to resist lateral forces without sliding, overturning, buckling, or collapsing. So here you can see in this diagram, we have our lateral load that's coming this way. So our load is basically a measurement of the lateral force that is hitting this structure from the side. Okay, and also this structure is also going to be experience some gravitational load downward on it. So when you get both of those together and the force is too much, you can see that the frame becomes distorted and it could even fail and totally just fall apart. So what we do is we will add in bracing. Okay, so a lot of structural frame structures, they will have some sort of like diagonal bracing integrated into them to prevent that from happening. So as this force now comes in here, basically the force is being transferred diagonally down to this point, and you don't have any of that distortion going on. So that's going to restore the stability within the structure. All right, a buttress. This is a thickening in a wall that provides extra structural support. So if you look right here at this cathedral, they have these buttresses right here. So these are basically just big thickened portion of walls that they have that are basically pressing against, or they're propping up this wall in place, and they're just helping to strengthen it. There's another type of buttress which is common in like classical architecture. I think like Gothic, maybe they use it a lot, but that's called a flying buttress, and it looks similar to sort of what you're seeing here, except they basically look like arches. So this area right here will be like hollowed out, and it'll just look like a big arch that's coming up and supporting it. So if you were just to Google flying buttress, you'd see exactly what I'm talking about right away. Cross walls. So these are walls that run perpendicular to a load-bearing wall. And the purpose of these is to just help the load-bearing walls do their work and support the structure. Shearing forces. So a shearing force is a force that describes two parallel surfaces moving in opposite directions. Okay, so you can compare this to like a pair of scissors, right? A pair of scissors, you refer to those as shears. And the reason they're called shears is because they exert a shearing force. And so if you were to cut a piece of paper, you're placing that piece of paper between the two blades of the scissors, and as you sort of move the shears together, they're forcing the fibers of the paper in different directions, and that's what causes the cut to occur on the piece of paper. Shear walls. So we mentioned this actually in the last module, but these are a wood, concrete, or masonry wall that is constructed to resist shearing forces. Their purpose is to transfer loads to the foundation and resist changes in shape. Okay, so you can see here we have an example of a shear. So we have a force coming from the left and a force coming from the right, and that makes whatever element this is, if it's a piece of paper or if it's a building structural element like a wall, it's going to cause that to want to split here at the midpoint. So they can also, what they mainly do is you have a force that's coming in here at the bottom, force at the top, and over time that's going to cause a deformation to occur. So here's the original shape, and then this dotted line sort of illustrates over time what's going to happen to that. So it's going to move to the left and then be deformed and not support the structure as well as it had originally. Twisting forces. So we use brace frames using diagonal bracing members to resist twisting forces. The taller and thinner a building is, the more likely it is to sway, and it's more subjected to twisting forces, so it needs more bracing built into it. All right. Next, we have grid frameworks. So when the structural systems of large and complex buildings are being designed, they will use grid frameworks to organize sort of the structure. So if we go on here to the next page, grid frameworks organize the columns and beams in a grid pattern, and they are intended to evenly distribute loads. The spaces between the grid frameworks can be divided using non-load-bearing partitions. All right, so if you look here at this drawing, this is a drawing from like Revit or something, but basically what you're seeing here is a series of columns, okay? So the columns are occurring on these sort of grid line intersections. So we have some dots here, 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 and here, and here, and here, and then again, here's another row, and all these little dots are representing basically columns, okay? These dashed lines are the column lines or the grid lines, and these will be denoted using letters and numbers. So you can see here we have grid line A, grid line C, grid line D, grid line E, grid line F, and then here we have 1, 2, 3, 4, 5, 6, 7, 8. So what you could do is basically then assign each column in this grid array an identifier based on that. So you could say column A1, I'm talking about the column that is occurring here at this corner. Column C3, that's going to be talking about this column right here, okay? So that's how we basically organize large complex buildings. We use sort of a grid array like the one you're seeing here. And that's something you're going to notice a lot on construction drawings whenever you're working professionally. Your CD sets that are worked on by you and architects, they're always going to have, well, depending on what type of project you're doing, most likely they will have plans that have a similar grid setup to what you're seeing here. Next, we're going to talk about service cores. So buildings are basically divided, well, commercial buildings, they're organized in a way where you take different building systems and group them together in a singular area of the building. And that just, the reason you do that is for efficiency, okay, and ease of maintenance, things like that. But basically, building systems of multi-story buildings are organized into service cores. These are essentially groupings of the equipment that support various building functions. So electrical, mechanical, plumbing, HVAC, etc. You're going to take all these things and you're going to group them together in one spot, just for efficiency purposes, like I said. These service cores will contain chases. And a chase is basically a shaft that carries pipes, wires, and other building components, ductwork, things like that, from one floor to the next. Okay. The locations of service cores is usually consistent from one floor to the next, and there are a wide variety of common service core layouts, each with their own sets of pros and cons. So the textbook is going to explain these a little bit more in depth, explain the pros and cons to each of them. But if you look at the basic layouts that we have listed here, you can see we have a single core, which is just a core right here in the middle of the building. Here's a core at the edge, so at the top edge of this building is where that's placed. Here's two symmetrical cores, so basically you're taking the core, you're cutting it in half, and then you're having one half of it on one side of the building and one half of it on the other side of the building. Multiple cores, again, here's 3 of them at the edge, and then you can even have a detached core where the core itself sits outside the building, and then all of the wiring and the pipes and the ductwork, these are service runs run into the building from the outside. The downside to this one is the service runs can be pretty long on them sometimes, but on the upside, you save a lot of the interior space of the building because you don't have all that mechanical equipment taking up all that space. All right, so it really just depends on the project, what type of service core will be used. This here shows a plan drawing that shows a central service core. So if this were like an office building, for example, you would have all your, mechanical equipment, your elevators. These are elevators right here. You have your stairways, your vertical circulation paths, your electrical wiring, your plumbing chases. All of that stuff is being grouped here at the middle of the building. And then the entire perimeter is going to be dedicated to like your office space, for example, if it's an office, or apartments, whatever. All that stuff is then going to be grouped here on the exterior. Okay. All right. Now we're going to talk a little bit about specifically different structural types. Okay, so we have first light frame structures. So framing is the process of fitting and connecting relatively slender members to shape and support a structure. Light frame construction, this is framing that is comprised of closely spaced structural elements made of dimensional lumber or light gauge steel. All right, so these are often built on site from local materials. You can think of light frame structures as like residential structures, so like houses and stuff like that, usually light wood frames. Again, this is what I was just saying. Light wood framing, this is the most common framing material for residences. Sheathing, this is a material that is applied over top of the studs on the exterior side of an exterior wall. It's made out of plywood or other panel materials, and it's used as a basis for siding, flooring, or roofing. And then over top of the sheathing, they will apply like the Tyvek air barrier, and then over top of that, they will put the siding. Okay, so the siding, that's an exterior facing material installed over the sheathing, and it can be a variety of materials such as wood, vinyl, or metal. All right. The next few pages, I'm going to be showing you some examples of the different types of wood framing. So the textbook doesn't really show you these. It just basically talks about them. So I figured I would replace all that with these diagrams so you can kind of understand what these look like. Okay, so first we have the post and beam foundation. And this is like a very old type of structure. Okay, so you can see here, basically it's all made of dimensional lumber, and you have these vertical members, which are called the posts. Okay, and these are resting upon sort of a sill plate here at the bottom. So these horizontal members, and then your floor is going to be put on top of that, and then that's going to go up to these horizontal members that are supporting the roof structure. And then we have these purlins here that are connecting all of the, rafters. Yeah, these are called rafters in this case. It's all being sort of like held together, sort of like sticks, basically, like a stick structure. So then moving on from that, this is kind of like a really old style that they used historically. But then moving on is the plank and beam frame. So this is a more modern style, and it utilizes a series of planks connected with regular framing members. So we have our vertical posts here underneath each rafter that's going to be transferring the loads down to the foundation. We have floor beams here, number 8, and these are, think of these as like basically your joists in a house. So you have these beams that are doubled up, and these are made of standard lumber, and these are supporting the floor, which is made of a series of planks, and then the roof here is also made of a series of planks, right? Moving on here. So this is getting more into regular framing that you see with like houses. This is a balloon frame, an example of a balloon frame, and the reason they call it a balloon frame is because it's kind of like flimsy and lightweight, and they compared it back in the day to a balloon, saying like it could just blow away. And the walls on the exterior are 2x4, which modern walls are not that thin. Usually they're thicker than that to allow for like a proper R value and for proper structure. But basically, balloon framing is kind of outlawed. Like, you don't build houses like this anymore just because it's not that great of a structural system. Okay, but in a lot of older houses, you're going to come into contact with this. You can see here, if you look at these joists that are running, so these are the joists that your floor is going to sit on, your first floor. The joists are split, okay, and they kind of butt up to each other. And then where they are split, there is this large beam down in the basement that is going to be carrying the load of those, okay? So they are sitting right on top of that beam, and that beam is going to run from one end of the house to the other. It's going to support all this weight here. But they, back in the day when this was common, things like dimensions and stuff were arbitrary. They kind of just like put things where they decided to. There weren't as stringent of standards. So like you can see here, they just would overlap the joists and stuff like that. There's a lot of weird things about balloon framing that they used to do. I'm pretty sure this is what my house is. So again, I've talked about my house in the past, but it's a really old house. And if you come into contact with like really old houses from like early 1900s or late 1800s, they will probably have this type of a frame structure associated with them. So now here's a platform frame. This is a lot more in line with what we're used to nowadays. So a platform frame came about as a ways to simplify the framing process and to develop something that was a more economical and just a better structure, like worked better. So they ended up coming up with this in the late 40s. And basically, you're building your floors as like a series of platforms, okay? And the platforms are resting upon they're resting upon, here in this case on the first floor, the foundation wall. And then you have your exterior walls coming up, and then you have another platform, okay? So you can see here, the floors in this case are, they have a subfloor that's made of either plywood or like OSB, oriented strand board, if you've heard of that before. But this floor sheathing material is going to provide a smooth subfloor for sheet flooring. All right, and then you also have a sheathing here on the roof over top of the rafters that your roofing shingles will be applied to. And the frame elements, these are all standard, going to be spaced 16 inches on center. Okay, so that means the center point of each of these studs is going to have a standard dimension between them of 16 inches. Okay, so that's kind of the modern standard. And then here you can see, comparing this to the balloon frame, these joists that are coming through here, they don't overlap like they did here. They're actually butting up to one another. Well, they're butting up to this additional board that's running down between them. And then all that is sitting upon, again, these three large beams that are sistered together right here. And then those are then sitting on top of steel columns that are running down to the basement floor. All right, so our next and last little diagram that we have here for the framing. This is what's known as a advanced frame system or an OVE system. So this was developed toward the late 70s, and this is basically a lot more engineered than the previous examples. Okay, so this has a lot more of like an engineering and scientific technology associated with it. So OVE, that stands for optimum value engineering. And this, again, was a way to make things more economical. So reduce the cost of building houses, but also provide a way to create the structure of the house so that it is solid, while also saving money and materials. Okay, so if you look here, for example, one thing that they do in this type of a structure is the joists, the floor joists, are not solid wood. These are those I-joists that I actually mentioned previously. So what they do is they have two pieces of wood on the top and the bottom, and then this yellow portion here is actually a piece of plywood that is vertical, sandwiched between the top and the bottom piece. All right, so that is going to use less wood than just a solid joist that's going to be running through here. But also, the way that they engineer these they're usually actually stronger than just a regular solid piece of wood. So they do a lot of things that actually cut down on the amount of material that's being used. Okay, so we're using less wood in this case, but it actually has the same structural integrity as something like this, or it might even have a better structural integrity because it's supported by all this modern technology and research that we've done in order to engineer these to be a lot more structurally sound, and also they save a lot of money, again, because you're not using the amount of material that you typically would. Here you can see that we're using trusses instead of regular just rafters here, so the structural integrity of these is going to be a little bit better than what it would have been with older methods of building. And again, there's a lot of similarities between them. It basically comes down to kind of the technology and the approach, but they're all just refinements of each other. So this is basically just our basic standard, and then we moved on to this, and now we're more somewhere in here where we're engineering things to a higher degree. All right, we also have heavy timber structures. So these utilize large wooden posts and beams. They're more fire resistant than light wood framing, and heavy timber construction that is combined with brick is known as mill construction. On top of that is pole construction. So these utilize piers made of pressure-treated wood that are firmly embedded down into the ground, and these allow buildings to be built on top of steeply sloping land without needing to clear out the land and flatten the grade. So moving on from the wood, we're now going to talk about some light steel framing. So light gauge steel studs are manufactured as channels or C-shapes, and they contain punched holes that allow piping, wiring, and bracing to run through them. So if you look at this example of a steel stud here we have our studs, and then these are basically resting in a C-channel sole plate, and they're screwed right there with a fastener to hold them together to that bottom plate. And then right here are these holes that they have punched in them. And these holes are where you run your electrical or your plumbing lines, okay? So you'll run that from horizontally from one stud all the way through the next. Steel studs are lighter, stronger, more dimensionally stable, and they can span longer distances than wood. Okay, so the thing about natural materials like wood is they will expand and contract at like a more significant rate than like a steel will. So if you have a piece of wood, it's going to change the size of it based on a series of conditions. So for example, temperature will cause the wood to either expand or contract, and also moisture. Okay, you have to take these things into consideration, because because you put something together one day and it looks good, maybe over time it'll contract or it'll expand, and that will sort of change the way it's being held together. So like if you have like a wood floor and it's subjected to a lot of temperature changes over time, the fasteners that are holding it together, that shrinking and expanding, can cause like the nails in the floor to come loose. So if you're like in an old house, for example, and the floors creak, that's why, because over time the wood flooring has expanded and contracted, and that movement of the structure has actually pulled the fasteners loose. And when you step on it, you're actually hearing it rubbing you're actually hearing the nail rubbing in and out of like where it was originally. Okay. So the thing about steel is it's more stable. If you were to subject it to temperature changes, it's going to take a lot more than wood to sort of distort its dimensions. Okay. Masonry structures. So masonry is one of the oldest structural types there is. Masonry units can be different materials such as brick, CMU, that's concrete masonry units, or clay tile. A single row of a masonry unit is called a course, and multiple courses stacked on top of each other is called a field. Continuous vertical sections of a masonry wall that is 1 unit in thickness is called a withe. So if you were to look at this here, this is the a figure from the Bengali book. Here is a what's known as a withe. So there's one there, and then there's also one here. Basically, that's just referring to the layers of this wall assembly. So we have a layer of like CMU in this case, this big block here, and then the smaller brick that's in front of it, that is its own withe. And then we have a course. A course is basically just a single row of bricks. So this darker gray line of bricks here, that is a single course in the wall assembly. And then the field is basically multiple courses stacked on top of each other. And then we have joints between each of these masonry units. The joints that are between the masonry units are filled with a material called mortar. And in grouted masonry walls, 2 withes are bonded into a single mass using grout. So grout is basically just thin mortar. Cavity walls, so these are basically masonry walls that have multiple withes, so like this, but they're not directly on top of each other and they're not bonded to one another. They have a cavity between them, which is basically just an open air space, and the purpose of that is to keep out water, and it may also serve as like insulation. Okay, so the last module we talked about air spaces between wall cavities a little bit, but just the dead air between 2 layers of a wall, that is going to act as a natural insulator. Okay, and there's code requirements for how big the airspace should be. Okay, so the distance between these 2 withes is at like 2 inches, and that's going to vary depending on, a bunch of different factors. Walls that have non-structural facing of stone, brick, or concrete, or tile, so these are known as veneer walls. So a veneer, basically that's just a general term for something that's just applied cosmetically over top of something else. So, for example, you could have like wood veneers. What that is, if you don't know, which you probably do from like your furniture classes and stuff, that's just taking a crappy piece of wood, so maybe like a piece of plywood, and then putting a thin piece of a really nice wood over top of it, so that's not solid all the way through. Basically, that just helps with like the cost and stuff. But that's a veneer, okay? It's just something applied over top of something else that does not serve a structural purpose. The minimum thickness of a load-bearing or shear masonry wall is 8 inches if you're not using a reinforcement. But if you're reinforcing the structure of that wall, you can get it down to 6 inches. Okay, masonry walls also have movement joints. This is a general term. You may also hear the term control joint or expansion joint. And what these do is they allow the materials of the masonry wall to expand and contract due to changes in temperature and moisture. So for example, clay will absorb water and it will expand, and concrete, as it cures, it's going to naturally shrink, okay? Movement joints are incorporated into masonry walls to control dimensional changes within the walls. They close slightly when masonry expands, and they open slightly when masonry shrinks. Masonry walls do not contain movement joints can fail over time. Okay, so they can kind of like just naturally fall apart because they're expanding, contracting, and there's nothing there to control that. So here, if you look at this picture, this is an example of a movement joint. That's this line that's running here through the center. Okay, so basically they will just make a cut that runs all the way through there, and then that's going to basically control where a failure would happen if one were to occur, and that just keeps the structure as a whole from failing. So in terms of masonry units, there's several different types. We have stone masonry, brick masonry, CMU, concrete masonry units, and glass block. All right, so here are some examples of the different types of bonds that you can have. So if you're stacking brick, there's different ways that you can stack them on top of each other, and that's what's known as a bond. So this one is probably the most common. It's just called a running bond. This one here is called a common bond, where you have like a running bond mixed with these smaller brick courses running through them. Then we have an English bond, which is sort of like an alternating a running bond with a common bond. And then we have a stacked bond, which is just where you stack the bricks directly on top of each other and you don't like stagger them. Concrete structures. So concrete has been used as a structural material since the Roman Empire. Aggregates, these are materials such as sand and gravel that are added to concrete to increase its strength, weight, and fire resistance. Cast in place concrete. So this is when you take concrete and you create like a form for it. So you can see this example down here is for a set of concrete steps. They take and they will build up these wooden forms, and then they will fill that full of some crushed gravel, and then this right here is actually rebar. So this metal wiring that's running through there, that's to add some structural integrity to the concrete itself. But once they have all this in place and they have the form built, they will then pour the concrete in and they will let it dry and cure, and then you'll have your finished steps. But that's what they mean by cast in place. You're creating a form where it needs to go, then you pour the concrete in, and then when it's all dry, you remove the forms and you have the finished steps there. So cast in place concrete is common in concrete floor slabs, foundations, sidewalks, and concrete stairs. Tilt-up construction. This is a construction method where concrete wall panels are tilted up by cranes and they're placed in position. A benefit of this type of construction is it provides good structural strength, insulating value, thermal mass, fire and weather resistance. So here's an example of tilt-up construction. You can see they have these individual panels that they will pour, and then once they are dry, they will take a crane and they will hoist them up into place, and they'll butt them end to end. Precast concrete. This is when you have concrete components that are cast in an off-site environment, and then they are then transported to the site and they are set in place by cranes. A benefit of doing it this way is it offers consistent strength, durability, finish quality, and it will reduce on-site formwork. Metal structures. So we mentioned this a little bit ago, but steel framing. So these utilize steel beams and columns that are spanned by open web joists. Okay, they are most effective when they are arranged in a regular pattern of girders, beams, and joists. So if you look at this diagram here, I pulled this from the Ballast book. Basically, a girder is this element running horizontally here, and you have beams between the girders that are spanning this opening. Okay, and these are spaced based on code requirements. There's going to be a standard spacing of all these, and then the girders are sitting on top of these steel columns. All right, and all this is basically arranged in a grid, just like we talked about previously. So these column lines, these will all be arranged by the engineer in a way that makes sense structurally. They can also be supported. So you're going to also have, instead of just a column, you might also have a load-bearing wall. So here on the right, you can see we have a load-bearing wall. And then here we have a girder, but in this case, instead of just these beams that are running across, we have what are known as open web steel joists. Okay, so these are a type of joist where basically you have this a top chord and a bottom chord of steel, and then the space between them, they're being connected by this zigzagging metal structure. Okay. And this is very common in like large, like wide open buildings. So for example, like a warehouse or something, you'll probably see like a steel web joist system, because these can have pretty big spans. So you can have a wider distance between your columns. So anything that's like really big and has to be wide open, often you'll see like a steel web joist system. If you were to go to like Walmart or like a store like that and you look up, this is most likely what you'll see. Okay. Metal decking. So metal decking is a corrugated metal sheet that is installed over top of floor joists. And what they do is they will pour concrete into these to create concrete floor systems in commercial buildings. So this is what they look like. Typically, they have this ribbed pattern to them. Okay. And they're corrugated. The ribbing is what's known as the corrugation. That's the shape that you're seeing here. And the purpose for that is to add rigidity to the structure of them. If they were just a flat plane, they would not be as structurally sound. By actually adding this sort of zigzagging that they do, it makes them more structurally sound. And then the space on top of these, so over top of this would get installed right on top of the floor joist. So if you imagine this open web structure here, these floor joists, directly on top of that is going to be this, but the lines that you're seeing here will run perpendicular. Okay, so that's going to run this way right on top of those floor joists perpendicularly. And then on top of this is actually a layer of concrete that they will pour on, and the entire structure is just going to support that concrete. That's where you get your concrete flooring from. For example, in the CAED building where you have a concrete floor on all the floors, and it's most likely using a system like this where you have sort of this steel pan, this metal decking, and then they're just going to be pouring the concrete in on top of it. All right, so lastly, we have a few other basic structural types. We have a shell structure. This is a thin curved plate structure designed to transmit applied forces by compression, tension, and shear. Here's an example of one. So basically you can see it's just this very thin shape. Okay. A cable structure. So this is a structure that uses flexible wire or rope or metal chains with high tensile strength as a means of support. So think of a bridge or something like that. Here's the Brooklyn Bridge, and it has all these cables that are all connected here at this singular point, and then they're coming down and they're supporting the actual bridge surface below. Okay. And then lastly, we have a membrane or a tensile structure. So this is a thin, flexible surface that is going to transmit loads primarily along lines of tensile stress. Okay, so you can think of things like tents or any kind of like a tent-like structure like this. That is an example of a membrane structure. All right, so that is it for this lecture. Like I said, there's a lot of stuff in this chapter. It's not very many pages, but it's got a lot of content. So that took a while, but we got through it. Go ahead and read the chapters. Make sure that you understand all this stuff. And if anything comes up, let me know and I will help.